All right. Well, welcome everybody. I'm going to go ahead and make the introductory remarks here and buy everybody a few extra minutes to get connected. So let me begin by welcoming everybody back to the SMU Physics Department Speaker Series for Fall 2020. This is our penultimate event in the series for this semester. So this is the last week of classes, although there are no classes today and tomorrow. Exams begin next week. We're definitely getting to the end of the semester, and it's nice to conclude our November series and its theme of New Frontiers in Physics with the presentations today. And today's a really special event because it contains two shorter presentations from two of our PhD candidates who were supported this semester through the department and the college to conduct research toward their PhD. These departmental research support opportunities are never guaranteed. They're sort of considered on a case-by-case basis. And they're especially intended for students who need to make substantive progress toward the completion of their degree and where it is likely that external funding to support their work can be obtained. So this allows us as a department to try to bridge them forward toward their PhD. As a result of this, we as a department have a broader stake in their success. And today we will hear about the progress that they have made this semester. So each of our speakers will speak for about 20 minutes with introductions from their research advisors preceding their talks. So in just a moment, I'm going to hand things over to Professor Pavel Nadolsky to introduce our first speaker, Jing Xiaoxian. But before we get started, the quick reminders as usual. So to our audience joining us live and interactively on Zoom, to ask a question, you have to write speak in the chat window. That'll set up a little speaker queue. We can interrupt the talk during the presentations by each of the students today. We'll just catch them at the next slide boundary and let them know there's a question and then unmute you. Or you can save your question for the Q&A at the end, which will come after the two presentations. All right, so it's sort of up to you. And we are live streaming this simultaneously also on YouTube, but that's non-interactive. But nonetheless, welcome to our participants on the YouTube stream today. All right, so let me go ahead and welcome Professor Pavel Nadolsky to introduce our first speaker, Jing Xiaoxian. And while he's introducing you, Jing, you can go ahead and start sharing your slides.
Okay, very good. Thank you so much, Steve. So it's my pleasure to introduce Jing, who has been working with us on various interesting theoretical calculations, including the studies of the hadron structure. Now, for those who didn't attend the seminars dedicated to the structure of the proton, let me point out that many experiments in particle physics require to know very well what the protons are made of. And the protons are small but very fascinating objects. You can see a picture of one behind me. It's an artist's visualization how the proton looks like. You have to keep in mind that this object is very small and also has very unique quantum properties which need to be understood. Now, Jing has been with our group since 2016. And his main work is based on research done together with the so-called CTEQ collaboration. So CTEQ is a big group of researchers that study quantum chromodynamics and its applications at various domains. Now, Jing works with a subgroup within CTEQ called CT, and we focus on studying the structure of the proton, but also providing parametrizations for the protons that are used by many experimentalists. Last year, Jing spent I think 8 to 9 months at Jefferson Lab, which is a major national laboratory in the United States, where he worked with another subgroup within CTEQ called CTEQ Lab. And so that group focuses on understanding low energy effects in QCD. And so basically, their approach to the studies of the hadrons is somewhat different compared to what we do within CT. And it is very interesting to compare what we learned from the different studies of the experimental data, which are pursued both by CT and CJ, since what we find is that the fixed target experiments, like the ones that are done at Jefferson Lab or at the Future Electron Ion Collider, will continue to play a very essential role in constraining Parton distributions. For example, when you look at the Higgs physics production, you find that very important constraints on PDFs or Parton distributions in the region relevant for Higgs production come from the fixed target experiments. And what Jing has been doing in the past year, he was applying methods from data science to understand how constraints on the Parton distributions arise from a variety of experiments, including fixed target experiments. And so that's what he is going to present to us in the next 20 minutes. So Jing, I think you can start.
Okay, thank you for your introduction. Today my talk is going to be Parton distributions, nuclear deeply inelastic scattering, and electroweak precision measurements at the LHC. My talk will consist of 3 parts. First, I will introduce what the PDF function is, and I think most part has been discussed by Professor Pavel. Also, I will talk about the PDF fitting, how does it work? And eventually, I'm going to talk about the sensitivity methods, which provide us a deeper understanding of the PDFs and the experiments for the PDFs. First, PDF functions. So PDF, usually they take form of a set of functions with variable x and q for the quarks and gluons. They are needed for predicting a variety of processes at the LHC, including the Higgs boson production and searches for the new physics beyond the standard model. They describe the probability of finding a parton carrying proton momentum fraction at the scale q. On the right-hand side, we can see it is a typical PDF function, how it looks like. It comes with a central value and also the error band. The error band, it is also called the PDF uncertainty. It comes from the experimental measurement errors and also from the theoretical approximations. The PDF value itself is not observable that can be directly measured. So we related this variable to the measurable quantity, which is called the cross-section. The cross-section, it is related to the PDF through a convolution between the PDF function and the matrix elements of the various PDF or various physics processes, such as Drellian process. We know that there is no first principle prediction for the PDFs. So what we do is we come up with very different kinds of functions to fit the PDF. I've been working with the 2 groups as introduced by the Professor Pavel. They are the CTEQ and CTEQ lab group. In both groups, the PDF parameterization takes the same form, take a similar form. It is a polynomial function with some anticipated behavior at low and high x, which are represented by these parts. They also have lots of difference between these 2 groups. For example, the CT fit, it contains more data, and the treatment is at next linear order, but it contains no nuclear treatment. For the CJ fit, it is at next linear order, and it is specialized in the nuclear correction. The 2 groups, they also fit different set of experiments as shown in this table. What we need to do in a PDF fit is that we need to determine the PDF value at the initial scale Q0, which is approximately at 1 GeV. The PDF value at a higher energy level can be calculated through the PDF value at low energy level through the DGLAB evolution function. We need to determine the PDF value for various quarks and anti-quark and the gluon. Therefore, it contains a lot of parameterization parameters. For example, in the CJ15, it contains 24 parameters, and in CT18, it contains 29 parameters. Next, I'm going to introduce what are the experiments included in the CT18 PDF fit. As shown in this plot, we have the inclusive jet, WZ production, TT bar, and Z production. Also, Harris DIS, and fixed target DIS and Drellian. In general, these experiments can be categorized into these 3 types of physics processes. The DIS experiments, which is lepton-hadron scattering with exchange of a virtual photon and then later decay into a pair of leptons. The Drellian process, it happens when a quark from one hadron and an anti-quark from another hadron, they annihilate into a virtual photon or that boson and later decay into a pair of oppositely charged leptons. The jet production is similar to the previous process, but it produces a chrome of hadrons or other particles. The measurable variable in these experiments is cross-section. PDF, it acts as a bridge connecting the scattering amplitude and the cross-section. As shown in this slide. The cross-section of the DIS experiment, it is the convolution between the PDF function and the scattering amplitude of the hadron process. For the Drellian process, we need to convolute both of the PDF of 2 protons and the hard scattering matrix element, which is calculated by the theory. And jet production is all similar. We also just talked about the Higgs production. The Higgs production, essentially, it is similar. It is also interaction between 2 hadrons. Therefore, the Higgs production cross-section, it is a convolution of the 2 PDF functions of the protons and the hard cross-section, the hard matrix element here. So next, I'm going to discuss the flow of the PDF analysis. How do we assemble all the pieces we have talked about and come up with the PDF eventually? If we have the experimental data, or the cross-sections of various experiments, we also have the theory calculation of these experiments and the theory calculations that depend on the PDF fits, the FXQ, and the PDF functions that depend on the PDF parameters A. Therefore, with these 2, we can calculate the chi-square, total chi-square, which is going to be a function of the PDF parameters. Then we minimize the total chi-square, and we can obtain the final best fit PDF parameters, which is called the A0. With the A0, we can obtain the central PDF sets for various flavors and the total chi-square for central PDF set. If we allow the total chi-square along each eigendirection to increase by 10 units, we will obtain a set of error PDF sets, which is exactly the same number of 2 times the number of PDF parameters. This flowchart, it is quite complicated. Here's the reason. In each step, there are lots of sources of complexity. For example, the data selection, which experiments to be included in the PDF feed, the treatment of these errors, how do we treat the correlated and uncorrelated error. Also, different PDF groups, they have the different PDF parametrizations and the theory assumption for these PDFs, such as the flavor asymmetry or symmetry. The heavy quark treatment, do we use the fixed flavor or other scheme? Also, the behavior at low and high X. And on the theory side, the order of perturbation and the theory calculation method are also some complexity of this part. And for the minimalization process, different groups use different methods. For example, the CT group use a gradient descent method. For the CJ group, they use a metaquad method. And with all of these complexities, can we understand and compare the experimental constraints in the CJ and CT PDF feeds? Also, can one tell which modern experiments are the most constraining ones in the latest PDF feed? To answer this question, we apply the Hessian sensitivity method. The Hessian sensitivity method, one of the cases is the L2 sensitivity. So L2 sensitivity, it is the linear approximation for the delta chi-square of a certain experiment E when some PDF value increases by the 68% of confidence level of the Hessian PDF uncertainty. And it is very fast to calculate with good accuracy. Here are some results. If we wish to understand the Atlas weak mixing angle and its correlation with PDF flavor combinations, we can check this plot. So weak mixing angle, it is a key parameter in the electroweak sector of the standard model. From this plot, we can see the correlation between the weak mixing angle, it is closely correlated to U and D quarks. So if we wish to understand the U quark and D quark, also the weak mixing angle, we wish to understand which experiments they constrain the D and U, and what kind of treatment affect the D and U flavor PDF functions. Here we apply this method on the CJ group. In the CJ group, we try 2 kinds of fits, as discussed previously. One with a deuterium correction, which is fixed. The other one is without a deuterium correction. On the left-hand side, it is one without, and on the right, it is with a fixed deuterium correction. We can see that if we remove the deuteron correction, the tension between the two group experiments, essentially the gamma jet and the DIS deuteron, they can be very large, up to 30 units. And when we introduce the fixed deuteron corrections, the tension is reduced to a scale of 5. Therefore, we conclude that the nuclear correction reduces the tension between the different groups of experiments, which can lead to the reduction of the error band. We apply the same tactic, same treatment to the CT group, but we found that the scale is almost the same. We noticed that although the scale is quite similar, but the impact of certain groups such as the DIS deuteron is greatly changed. DIS deuteron, it is group 4, and we can see at high X the behavior changes a lot. Therefore, deuteron correction, it can affect the pulse of certain experiments. Eventually, we are going to talk about another type of treatment of the deuteron correction. We allow the deuteron correction to be fitted, which is a free deuteron correction. And we notice that in the CJ, if we allow the deuteron correction parameter to change, the tension is going to be reduced, and which may lead to the reduction of the PDF error band. Next, I'm going to talk about this method applied in the EIC yellow paper. EIC yellow paper, so here this plot shows the sensitivity of Higgs cross-section calculation on each data point of the EIC experiment data. The sensitivity is represented by the color of each data point. The result we see is that the constraint of the gluon and other PDF at the EIC will reduce the PDF uncertainty on the Higgs production at the LHC experiment. Also, if we wish to understand which data points they have the major impact on the Higgs production, we can just tell by the color. If the color is very red, that means these data points have a direct impact on the Higgs production. So to summarize my talk, we know that PDF sensitivity, it is a statistical indicator that visualizes the constraint from experiments on the PDF in CTEQ global PDF fit. I apply this sensitivity method to understand the origin of U over D pools with CT and CJ PDF fits. The pools are affected by the nuclear corrections in the fixed target DIS. The treatment of this nuclear effect in the PDF fits help us in understanding the uncertainties of the proton PDFs in high luminosity LHC experiments. So, okay, thank you for your attention. That is all my talk.
Okay, yeah, thank you very much, Jing. Let's try to give you a little applause here. I see Roberto clapping. That's very nice. Excellent, excellent. Well, so since you have your slides up, why don't we alter the bargain I said at the beginning, and why don't we open the floor up now for questions for you? That way you don't have to worry about bringing your slides up again later. So if anybody has a question, just go ahead and type speak in the chat window. I have a couple, but I'll wait and see if anybody writes anything there. All right, well, while we're waiting for people to think of questions, do you mind if I ask one, Jing?
Sure, please.
So on slide 5, you mentioned the importance of nuclear corrections, may need to be included in that CTEQ TEA doesn't include those, but CTEQ JLab does include those. And then you pointed out later how, at least in one PDF set, it seems to resolve some of the tension between different PDFs. How does one incorporate the nuclear corrections into this polynomial formula approach, or is that done separately?
To answer that question, we know that there's the nuclear correction. It is effective collection of some the offshore partons and Fermi motions and everything like that. We use a function to we use a polynomial which contains around 2 parameters to calculate the PDF function of the deuteron. So the deuteron, it is not just the sum of the proton and neutron. It is the sum and then plus polynomial as a coefficient. Does this answer your question?
I think so. So I mean, so it enters in then as modifications to the coefficient here with no other changes to the formula, or does it alter the formula in some other way?
No, it does not alter the formula here, but it alters the formula for the deuteron PDF.
Okay, so specifically it alters the formula for that specific PDF then. Okay.
Yes.
Okay. All right, does anybody else have questions? If not, I have one more for you, if that's okay. Could you go back to that nice slide you showed that you mentioned was something that had been done for the EIC yellow report? So just for the benefit of the audience, could you just briefly explain what is the yellow report intended to do? And then I'll actually get to my actual question. So could you just briefly explain what is the yellow report?
The EIC yellow report, it is a proposal on how the future EIC experiments, how it's going to affect the PDF error band for different PDF groups and certain flavors.
Yeah, so yeah, to sort of project the impact of the EIC. And some of that impact is potentially shown here. So the red points you said are especially impactful on the Higgs production calculations. Is that right?
Yes, that's correct.
Right. So, and these are all points that the EIC in principle should be able to cover with one process or another, as you've illustrated in the legend?
Yes. So they contains the neutral current and charge current of the electron, proton, and the electron, deuteron. There are different data points here.
Do you know roughly how much data has to be integrated for each of those to get the desired impact? Like in inverse femtobarns, do you happen to know roughly the size of data that's needed at the EIC?
I do know that the neutral current is around 100 inverse femtobarn, and the charge current is approximately 10. And the deuteron, it is approximately 10, and the proton is 100.
Okay, that's fantastic. Yeah, so it's not all just, you know, half a year or 1 year of data taking. It may be a little bit less or a little bit more in some cases then.
Yes.
Okay. Sorry, Roberto, you had a question. I think you can go ahead and unmute. So go ahead and ask your question. Oh, you're still muted, Roberto. Let me see here.
Is that good?
Yeah, that's fine. There we go. Good.
In the theoretical calculation of the cross-section, to what order, I guess it depends on the processes that you're considering, but I guess how sensitive are these results that you get for the fits on the order of perturbation theory that you use for the cross-section, and how in this procedure that you follow, do you make sure you don't double count contributions coming from the Parton distribution functions with higher order processes in your cross-section?
Oh, that is a very interesting question. So to my experience, what I have done with the CJ, what we did is to calculate next leading order. And in my experience, we performed the next linear order calculation with two methods. One is with the K-factor method, which is fixed. I mean, it's a ratio of the next linear order and linear order for each being is fixed. And the other method is the apple grid calculation. And with these two calculation for the next linear order, we find that the PDF central value does not change much. The error band does not change much, but at certain regions, it will have a noticeable impact. And to answer how do we avoid the double count of the PDF and the matrix, the scattering amplitude, I'm not sure about, I don't have the answer to this question right now.
That's all right.
Yeah.
I'm just curious.
I mean, there'll be time for you to think about it before we get to the end Q&A anyway. So maybe you'll have an answer later on.
This is defense.
What's that?
We will save it for the thesis defense.
Oh, nice teaser. I like that. Saved by your advisor, Jing.
That's good.
That's a good question. But Jing, let me ask you, like, for example, suppose, well, you see the PDFs and the hard cross sections, they depend on the parameters called mu. Right. So what is the purpose of this parameter? And so does it have any relation to preventing the double counting?
Oh, you mean the energy scale here?
Yeah. So in other words, you see both the PDF and the hard cross section depend on the parameter mu. So what is that? And does it have any role in preventing the double counting?
So first of all, the mu it stands for the energy scale here. And the PDF value, as we discussed, it is a function of it. The mu it is the Q here. It tells which energy level the proton is at. So at low, how does it help to avoid the multi-counting? Let me see.
Well, maybe it's too much to discussing, but you can think about it. So I think a part of the answer to Roberto is that, well, we introduced the special scale, and somehow it plays the role in preventing the double counting. And so, and then, okay, so one of your tasks is to figure out what it is and how exactly it works.
Perfect.
Yeah.
Nothing like having homework, right? All right, well, no, thank you very much. We can always come back if people think of other questions at the end after we've had a chance to hear from Yingnan and ask him questions. We can have kind of a general question period at the end in case somebody wants to go back and ask Jing something. So let's thank Jing one more time. So thank you very much, Jing. And I'm going to hand things over to Roberto now to introduce our next speaker, Yingnan Xu.
Okay, Yingnan graduated from Oberlin College with a bachelor's in math and physics. After graduation, he went back to China and tried his hand at teaching physics in high school. But he had been bitten by the physics mosquito, I guess, and he wanted to come back and do a graduate degree, and he came to SMU. And he's been one of the best students in my quantum class. So I was very happy when he asked me to work with me on a project. He's going to be talking about a simple extension of the standard model, and he'll tell you more about that. So I'll let him do the talking. That's it.
Okay, thank you. So today I'm going to talk about the dark photon theory, and here's the references I used for my research. So the motivation here is that we know that currently the most successful theoretical framework in particle physics is the standard model, but it's not complete. For example, it doesn't explain phenomena such as gravity, dark matter, and dark energy, matter, antimatter, asymmetry, etc. And it also has theoretical problems like the naturalness problem and hierarchy problem. So there are a lot of efforts has been made to extend the standard model into a grand unified theory, where the standard model is regarded as a low energy effective theory, and the standard model gauge group can be thought as a result from spontaneous symmetry breaking of a larger symmetry group. Most of the extensions lead to an extra UN gauge associated with the field, which we will call it a dark photon to the standard model. And this is just the simplest addition, and it is not the whole picture. The completion of it requires a dark sector, dark in the sense that fields in this sector do not carry standard model charges. But we will see that we can gain some insights on the dark matter recover couplings of fermions, etc. The dark photon, that field may be massive or massless, and we shall discuss its phenomenology separately. Massive dark photon is of particular interest for it couples directly to the standard model current, and itself can be a candidate for dark matter. So let's look at the theoretical structure. So the most general kinetic part of two UN gauge groups, the Lagrangian we can write down is this. So F mu nu here is just the normal field strength tensor. And you can see there is a kinetic mixing term of these two UN gauges, A and B. So the epsilon here it should be very small because we don't want it to affect our current physics. So it should come from loop suppressions. And we suppose that the field A sub B mu couples to the standard model current J mu, and A sub A mu couples to the dark current J prime mu. So the interaction Lagrangian we can write down is this. Because of this kinetic mixing term, we cannot identify the physical state. So we may rotate the kinetic mixing term away by orthogonal transformations like this, where we will identify this A prime mu as the dark photon and this A mu as the ordinary standard model photon. Okay. So then we have the Lagrangian like this. And this theta is just a rotational parameter and it is arbitrary. So we can choose sin theta equal epsilon so that the dark photon only couples to the dark current and the ordinary photon couples to both the standard model current and dark current. So that's the Lagrangian defining the massless dark photon. You can say that A prime mu only couples to J prime mu. And this A mu, the standard model photon couples to J prime mu and J mu. So the Feynman diagram correspond to this Lagrangian is this. So gamma is the standard model photon. It couples to standard model fermions F and fermions in the dark sector chi. And gamma prime here is the dark photon, and it only couples to fermions in the dark sector. You should note that the coupling between the dark sector and ordinary photon is called a millicharge. This E prime epsilon over the square root of 1 over 1 minus epsilon square. So that's for the massless dark photon. For the massive dark photon, it can acquire mass either from spontaneous symmetry breaking, which will correspond to the dark Higgs mechanism, or by the Stueckelberg Lagrangian. So that's the Stueckelberg Lagrangian. So this m square is the mass for the standard model photon, and this m prime is the mass for the dark photon. In this case, we do not have the freedom of choosing theta arbitrarily. We obtain theta by diagonalizing the mass matrix. We obtain sine of theta and cosine theta separately. But we still want the standard model photon remain massless. This delta here is m over m prime. So we want the ordinary photon remain massless, so we set m equals 0. And with this choice, the ordinary photon couples only to ordinary matter, and the massive photon is couples to both the standard model photon, standard model current and the so you can say that the dark photon couples to both the standard model current and the dark current, but the standard model photon only couples to the standard model current. So that the Feynman diagram corresponds to this Lagrangian. So that's the standard model photon couples to standard model fermions, and that's the dark photon. It can couple to both the standard model fermions and dark fermions. So since we know that massless dark. So now we will discuss their phenomenology. So you can see that, as mentioned before, the massless dark photon only couples to dark sector, so it interacts with ordinary matter only through operators of dimension greater than 4. So that's an dimensional 5 operator that we can write down. So here, E sub D is just a coupling, and this lambda 5 is a cutoff energy. This psi here is just a Dirac field. And sigma mu nu here is proportional to the anti-commutator of gamma matrices. This dm and de here are magnetic dipole moment and electric dipole moment separately. And this will correspond to a triangular Feynman diagram like this, where Q is dark fermions, and this little q is standard model fermions. This S here is a messenger field, and we believe that standard model current interact with dark current through such a field. So this S is bosonic. And so the first Lagrangian here is obtained from the second Lagrangian, so from this one. This Lagrangian is of dimensional 6 with the gauge group SU2 taken at the unbroken symmetry of the Lagrangian, and the standard model fermion grouped into doublets psi L and singlets psi R. So in general, we can have as many dark fermions as there are in the standard model. Dark fermions interact with the standard model via scalar messenger fields akin to the superpartner of fermions, as we mentioned before. So you can say that because there's a sigma mu nu here, so this kind of interaction actually involves a chirality flipping process. So I actually evaluated these two diagrams, and here's the loop function. So this xf here is just the mass of the dark fermion square over the mass of the messenger field square. And here, mu s is proportional to is obtained from the vacuum expectation value of those scalar fields. And lambda here is just the cutoff energy here. So matching this model to the Lagrangian before, these two Lagrangian, we can identify the cutoff energy as this. This V of H here is just the vacuum expectation value of the Higgs. So this process actually helps us explain the flavor hierarchy problem. If for each standard model fermion, there exists a massive fermion partner in the dark sector, singlets under standard model gauge groups and a set of scalar messenger field S, then the Yukawa coupling is generated at Van loop via spontaneous symmetry breaking. And due to chirality, the Yukawa coupling is proportional to the dark fermion masses. The observed Yukawa hierarchy just reflects the structure of the dark fermion spectrum. I personally don't really like this explanation because I think it merely translates the problem, the Yukawa hierarchy problem of the standard model to the dark sector. Okay, so here's the phenomenology for the massive dark photon and its relation to dark matter. So very light massive dark photon can be dark matter candidate if produced non-thermally in the early universe. Once the Hubble constant value drops below the mass of the dark photon, its fields start to oscillate and behave like cold dark matter. But we have two problems in this scenario. First, the initial value must be fine-tuned to reproduce the critical density. And the second is that decay into photons and standard model fermions must not affect the cosmic wave background. The latter requires the epsilon value. This epsilon is what we see in the first Lagrangian, the very first Lagrangian. The epsilon equals less than 10 to the minus 9, and the mass of the dark photon less than 1 MeV. So when the mass of the dark photon is heavier, such like it's greater than 2 times the mass of some dark fermions, then we have the annihilation channel to dark fermions annihilate into standard model fermions. And we are in a scenario of light dark matter. And I evaluated the cross section. So that's the cross section. So here, alpha is the fine structure constant, and alpha d is the fine structure constant in the dark sector. And this is not hard to evaluate because the whole process is just like the electron-muon scattering. So the Feynman diagram is like this. So the thermally averaged cross-section in the non-relativistic limit is this. So here we define the yield variable y equals epsilon square alpha d times the mass of the dark fermion over the mass of the dark photon to the fourth. So this yield variable is very useful because later we will see that it helps us to put constraints from cosmology. And this y, because this y is related to the Rayleigh density. So this omega sub chi is a dimensionless parameter. It's the density of the dark fermions over the critical density, and h squared here is just the dimensionless Hubble parameter. So here's the graph of the yield variable plotted as a function of the mass of the dark fermions. So you can see there are experiments like the light matter direct detection, like this one is CRISAT 2. And there are also beam dump experiments like this BDX. So that's blue dash line. And here we also have the experimental limits for the massive dark photon of mass less than 1 MeV. So you can say that we have atomic and nuclear experiments which aim to detect modifications of the Coulomb force due to dark photons. Those are basically around this area. So you can see atomic spectra and Rydberg experiments. And there are also experimental limits from cosmology. So you can see that Kobe and Firas and that's Santi, I think that's the neutrino experiment from the sun. Okay, so to draw a conclusion, so the dark photon theory is a low energy effective theory, and its completion requires ending a dark sector. The answer to the Yukawa coupling problem is unsatisfactory, as it merely translates the hierarchy problem to the dark sector. Massive dark photons can be a dark matter candidate, yet it introduces a new naturalness problem. In this review, we are more interested in dark fermions as dark matter candidates. There are also models where dark photon couples to the inflation, and its final abundance is dependent on its mass and Hubble parameters. In this model, dark photon can still be a viable candidate for dark matter. And you can see there are a lot of constraints from collider physics and cosmology, but the most stringent constraints come from cosmological observations.
Okay, yeah, no, thank you very much. Let's try to give you a little applause here too as well. So Roberto's reliable for that, very good. All right, let's open it up to questions from the audience. Any questions? Anyone want to ask? Don't forget to type speak in the chat window. We'll get you unmuted. Oh yeah, Richard has one. So let's get down to Richard. And okay, Richard, you should be able to unmute.
Could you say something about the spin polarization of the massless dark photon?
The what?
The massless dark photon. Does it have the spin polarization structure?
Oh, actually, I didn't read things about the spin and polarization of the dark photon, but I think I'll find something later.
So there is no effect of the spinors in this calculation?
Which calculation?
This model, there's no, these photons are not polarized like they are in the models that he referred to at the end there that are coupled to inflation. Those models, there are these polarization effects, but not in these models. Mostly these dark photons are not good candidates for dark matter or any of that sort of stuff.
Thank you.
All right, Pavel, you're up.
So Yingnan, maybe we can go to the summary slide showing various measurements that look for the dark photon.
This one?
Yeah, so what's next? Again, if you were just to give your opinion, like you said, for something about the flavor of the spectrum of the dark sector, but you could also perhaps say something about future interesting measurements. What do you think is most interesting and promising? And if you were to contribute, what would you calculate, or what would you try to predict?
So actually, later I'm actually going to focus on these models I mentioned here, where these dark photons can couple to the inflation and be a viable candidate for dark matter. So basically, I'm going to focus on this kind of models. But here, I think I just presented like a very general introduction for the dark photon.
But where will this model be, for example, on this plot? So like you have the coupling and you also have the mass. So where could these models lie?
Yeah, so basically, I think it still requires that the mass is less than 1 MeV. But so those color regions are, so the existence of the massive dark photon are excluded by the color region. Mm-hmm. So I guess we have to focus on those blank regions.
And you don't have a preference where you are in that white space? Which is okay. I'm just curious. So it's,
well, I mean, related to your question, Pavel, I was trying to understand what that green line labeled dark matter means. Is that the line that's consistent with the relic density of dark matter, or is that something else? And does that answer Pavel's question then, I guess?
well, maybe again I can rephrase. So here you show results of the experiments, but of course you also talk about cosmological implications. And so what I'm trying to guess is that do you just look at the very, very early universe, or are there measurements that can probe that specific range of epsilon and ma prime? Or yeah, so again, so what is the essential interplay between the particle physics experiments and cosmology?
So you can say that, so in this case, you have the yield variable, right? This is actually inversely proportional to the relic density. So I think that's the connection between the abundance of the dark photon and cosmology.
Oh, yeah, yes, but the question is, do you just focus on cosmology, or do you try to make predictions for the experiments as well?
So here, I think, I think I think I'll make predictions, yes.
Okay.
I want to hear your answer to Steve's question.
Well,
The green line for dark matter.
yeah, I think that comes from the yeah, I think that comes from the relic density, yes.
So then is everything above that allowed by our current knowledge of the relic density?
Yeah, I think it's below that.
Everything below that is allowed by our knowledge of the relic density.
Yeah.
Okay. So yeah, that, I mean, on that plot that you have your mouse on right now, then not a whole lot has really been ruled out. And,
so sorry, finish, Steve.
oh, and I was just going to say, and then in the bottom plot, it covers it slightly. Yeah, it covers a different decade range, right?
Yeah,
so there's still lots of
actually
opportunity.
just a magnification of that part.
Ah, okay.
Sorry, Yingnan, but can I ask, that, do you assume that there is just one type of dark matter, or it's dark matter in general?
So here I just consider the possibility of dark photon as a dark matter, but I think there are actually a lot of forms of dark matter, like axions and particles in the dark sector. So there are other possibilities, yes, but I think I here just focus on the possibility of dark matter as a dark photon as a dark matter candidate.
Okay.
I mean, on that subject, so you mentioned earlier in response to the questions about making predictions for experiments, but you know, dark matter with a mass of 10 to the negative 18 MeV is going to affect experiments in a different way than dark matter with a mass of, say, 10 to the negative 2 MeV, where maybe direct detection is more sensitive. So there's, you know, there's axion experiments, there's CMB experiments, there's tons of different experiments with all kinds of different ways of looking for effects on here. Is it really practical to think you're going to make predictions for every single one of those? Or in other words, is it better to concentrate on something? And you kept coming back to cosmology, which may be an interesting avenue if it's not so constrained yet.
Yeah, actually, I think yeah, I think so. Yeah, the most stringent limits are from cosmology, and I think I'll focus more on the cosmological part.
And just out of curiosity, so this is only your 5th semester at SMU, right? So you've just began your research effectively half a year ago.
Yes.
So you're very early in the process, whereas Jing is a more senior student, so he's much further along, closer to the PhD than you are. So this has been kind of a ramp-up period for you. And I'm curious, you did mention some places, I'm just taking a look at my notes here. Where did I note the slide? Maybe can we flip back to where you were talking about the Yukawa hierarchy, the Yukawa coupling?
Yes.
Was that something that you uncovered in your work, or did that come out of the references that you cited at the beginning?
Oh yeah, that's actually comes from the completion of the dark sector. So it actually from the references.
Okay, all right. So then, all right. So what things in here so far, if anything, and don't feel bad if the answer is nothing yet, because you're still early on. What things in here represent unique work that you've been able to do so far, even if it's something as basic as one of these calculations, one of these cross sections? That would be interesting.
So most of the calculations here are yeah, I evaluated most of the equations here.
Yeah, I guess where I'm going with this is
you're not original.
Okay, that was my next question, Roberto. Is there some kernel of something original in here that you see expanding out into the future? I was trying to look toward the future here with a question. You've been asked about where you're kind of going with this next. I mean, what is the next thing you want to do? Like, what do you want to do in the spring, for instance? I'm putting you on the spot. I recognize that. But it won't be the last time somebody does it to you. I mean, is there a question left over at this stage that you would really like to answer that you want to focus on next? And just to make sure we're not having technical problems, are you able to speak, Yingnan? It's been real quiet.
Yeah.
Okay, there we go. Okay, good. I just wasn't sure if it was thinking silence or technical silence. I mean, you've mentioned cosmology, right? So one natural place to think about these kinds of theories is for the next generation of CMB experiment. What constraints might those experiments place on these models if they don't see deviations in polarization from what's expected, right? What would be the signatures of a dark photon appearing, say, in CMB data in the next generation of experiments? Is that something that you've thought about yet?
He hasn't thought about that because these occur in models that he has not studied yet.
Okay. So there's more investigation.
That's the direction I want to point him in next, to look at those models and see there are polarization effects as Richard mentioned, and these dark photons appear in coherent modes, which certainly must have some measurable effects on the CMB.
Okay, so that would be, but that's not something anybody's really calculated yet then.
I think there are some papers out there that are looking at that.
Okay. All right, no, very good. All right, are there any other questions? Pavel, you had another one? Sorry, I just saw you.
Just to follow up on this idea of possible applications, well, clearly the dark photon models, they are very, very thoroughly being investigated. And well, right now we have an ongoing SNOMAS study, as well as the electron ion collider study. And both of them actually bring up the dark photon models and possibility to look for new signatures of this kind of models either at the LHC or at the electron ion collider. And so now at the LHC, you will be looking in the forward direction. And so there is a so-called forward physics facility that has been proposed. It is located in the tunnel close to the Atlas detector, but it is very far from the Atlas detector itself. And you could try to look for evidence from, like for example, well, of course, you will have neutrinos produced in the forward direction, let's say from charm decays inside the Atlas, but you could also try to look for evidence for the dark photon signatures in that direction. Now, at the EIC, we have this unique opportunity to have polarization, and that's precisely the opportunity to address Richard's question, because you could try to look for models that, essentially they have couplings that depend on the spin of the fermion. And again, I think there is plenty of opportunities to try to write a potentially easy and quick study, but we will address some of the issues, and it will be contributing to the EIC physics program that is being developed right now. So I think clearly there are opportunities to think about it, and so again, maybe we could discuss it sometime. Well, whenever we meet, or we can do it remotely. And so
yeah, no, that I mean, having a little convocation on this amongst interested parties is certainly encouraged. But this is certainly a nice level of investigation, at least pointing out the features of these models and where there may still be opportunities left. Because as you showed in those plots, Yingnan, there's a lot of space potentially left to explore, and it presumably doesn't end at the bottom of 10 to the negative 17 on the millicharge, the epsilon parameter, right? I presume it can go lower. There's nothing that prevents it from going lower.
Yeah, there are actually a lot of proposed experiments, and
Yeah, but thinking about this broadly with Roberto and other people in the department about where your work could have maximal impact if focused and directed now towards something, that would be a very interesting question to explore in the next weeks, basically. So, all right, any other questions for Yingnan or for Jing? Going once, going twice. Okay, great. I don't see any more questions. So let me just thank the advisors, Pavel and Roberto, and the speakers, Jing and Yingnan, for these very nice talks. We really appreciate you doing this. This was very short and very punchy today, but very informative. And